Hello, and welcome to Chapter 3, Section 2. Today we talk about conditional probability and the multiplication rule. So first, conditional probability. So conditional, the word itself means like there's a condition involved, meaning like we know something about the problem that we wouldn't have known before. So conditional means that you're going to be given some sort of information first, and you're going to be finding the probability using that given information. So here's what the formula looks like. We've got some crazy symbols. But in words, this is what it's saying. We want to know if some event has already happened, what's the probability of something else also happening? And remember, we use letters that are capitalized to stand for certain events. So if event A was what we were looking for the probability of, then this like vertical line here is going to be read as given. So the probability of A given B is going to be the probability of A and B together divided by the probability of B. So my easy way to remember this is just and over given. But basically we are trying to find what is the probability of A knowing that B already happened. So B is like the information that they're already going to be giving you. So that's something you need to read for in the question itself, and that's always what we divide by. Okay, so I'm going to do a couple examples of this, that way we can kind of see how it's used. So first, I'm going to use cards in my example. I don't know how familiar you guys are with cards, because I know people don't play cards a whole lot anymore. However, it is still a useful skill if you ever, go to the casino and play casino games, or just in general, it's not bad information to know. So first, here's the question. I got two cards are selected in sequence from a standard deck. So in sequence just means you're drawing one after the other. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. So if you are not familiar at all with cards, let me give you an introduction. Alright, so as you can see, this is a picture of all the cards that are in a deck. In a full deck of cards, there are 52 cards total, which means for each suit, so like each suit is the different shapes that are within it. For each suit, there are 13 cards each. So the first suit is called clovers or clubs. The second row is called spades, hearts, diamonds. Okay, and as you can see, they go in numerical order from an ace, which is kind of like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's jack, queen, king, and that's for every single suit. So the queens and the kings is what I'm asking about in the question here. And then, so you can see there are 4 queens in a deck of cards, there are 4 kings in a deck of cards, and 52 cards total. So in our problem, we're given that the first card is a king. So if I were to write out my the question that I'm trying to answer in like math symbols, it would look like this. We're looking for the probability that we get a queen given that I got a king already. So I need to figure out what is the probability that I get a queen and king over the probability that I got a king already. Okay, so imagine this. Out of the 52 cards, the first card that I draw is a king. So now I already have a king. We already know this. Now, since we are calculating our probability, how many cards are left in the deck? If there's 52 total and I already took one out, now there's only 51 cards left in the deck. So the probability on the bottom, because we're already given that I already drew a king. Now it just makes it so that there's less cards in the deck now. And so now, if I still want to draw a queen, there are still 4 queens left in the deck, because all I've done is taken out one of the kings. There's 3 kings left in the deck, but still 4 queens, and that's what we're trying to find the probability of. So if there's 4 queens left in the deck, then that's how many I have to choose from out of the 51 cards total. So 4 out of 51 would be my probability here. Another example is this time if I have a set of data like given to me in a table, so something like this where I have a two-way table, we are studying a child's IQ with the presence of a specific gene in the child. So we want to find the probability that a child has a high IQ given that the child has the gene that was specified. So if we rewrite our question that we're trying to answer into like our little math format, we're given that the child has the gene. So that means the gene is present is what we're given. So that's always what comes after in our formula, after the vertical line. And then we are looking for the probability that a child has high IQ. So that's why that's out here in front. That's the probability we're trying to find. So then we're looking for, to complete our formula, on top we're looking for the probability that the child has high IQ and they have the gene. And on the bottom we're just dividing by the probability that the gene is present. So when we talk about and over given, high IQ and gene, if you look on the table, the people who have high IQ and have the gene is right here, those 33 people. So those are the people with both, so and. And then what's given is that the gene is present. And so here, we don't care about like whether they have the gene or not. We just want them to have the gene that's present. So that's this entire column right here. We're basically saying like we only care about these people. Out of all the people with genes present, how many of them have the high IQ and the gene? So the total number of people who have the gene present is the 72. That number at the bottom there in the total. So our probability then of finding a child that has high IQ and given that the child has the gene is going to be 33 over 72. And like I said before, we never need to reduce our fractions. This is it. And if you really want, you can write your answer as a decimal or a percent. Okay, so that's all I've got for the conditional probability, and in class we'll do some more examples as well. Then the next thing I want to move on to is the multiplication rule. But before we talk about the multiplication rule, then we also need to define independent and dependent events first, because depending on which one our events deal with, it changes the multiplication rule just a little bit. So first, independent events. Dependent events would be just the opposite, because independent, dependent, they are opposite things. So independent events just means that one thing happening doesn't affect the next. So the first event that happens isn't going to affect the probability of the next. Examples of this would be something like flipping a coin. If I flip a coin the first time, the next time I flip a coin, it's not like the coin remembers what I got the first time. The second time I flip a coin, the probability of flipping heads or whatever is still 1/2. No matter how many times I flip the coin, it doesn't change the probability at all of the next time I do it. So that's an example of independent events. Another example is if I roll a die once, get a 3 or whatever, and I'm looking for the probability of getting another 3, then it's still going to be the same probability as before, 1/6, because it's not like the die remembers, oh, I got a 3 the first time, let me not roll a 3 anymore. So that probability doesn't change the more times you roll the die or anything, so that's still considered independent. Another example, this one is less obvious, but if we go back to like that whole drawing cards out of a deck example, if I drew a card out, then earlier in the first example that we didn't put it back in. And so because we didn't put it back in, now there's less cards in the deck overall. So that actually changes the probability, because if you have less cards in the deck now, that changes the total number that your probability is going to be out of. But if you do put the card back in, then it doesn't change like what you started with, and so that counts as independent. So drawing a card with replacement, so you are putting the card back in because you're replacing it, then that counts as independent. So dependent would mean that the opposite. So the whatever happens first is going to affect the second thing that happens. So if I don't put that card back in, then this will count as dependent events, because the second time around when I calculate probabilities, the denominator of the fraction changes. Okay, now that we know what independent and dependent events are, now we can talk about the multiplication rule. So the multiplication rule is used when we're trying to do multiple things at a time. Like we've been talking about flipping a coin multiple times, rolling a die multiple times, drawing a card, and then picking another card. So like anytime you're taking multiple actions, that's when you use the multiplication rule. So think multiple actions, multiplication rule. So the multiplication rule says that the probability of A and then B, like if you're going to do event A and then follow up with event B, you would just multiply, because multiplication rule, multiply the probability of A with the probability of B. And so it's a little bit different depending on whether you have independent or dependent events. If you have independent events, you just multiply the two probabilities together. Easy, done. If you have dependent events, the probability of B is going to change. Like we said, if it's dependent, the whole point is that the second probability is going to change because whatever happened first affected the second thing. So if the second probability has to change a little bit, you just need to think about like, what's going to change about it? Is there like less items overall now? Stuff like that. So that's all that changes, but you're just multiplying the two probabilities together still. Okay, so let's do some examples so that we can see how this formula is used. So for example, two cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. Okay, so looking back at our deck of cards, we are looking for the probability of getting a king and then a queen. So first, we know we're going to multiply because it's an and then question. And then it also says without replacing. So without replacing means that we're not putting it back in. So now the second time when we draw a card, there's going to be less cards overall in the deck. So keep that in mind. These are dependent events. Okay, so first, we just need to figure out what is the probability of drawing a king. So we have 52 cards total and 4 kings in our deck of cards because it's all of these ones right here. So 4 out of 52 is the probability of drawing a king. And then multiplying, because this is the multiplication rule. Then drawing a queen. So this time, we've already drawn a king. So there are less cards in the deck now. Because I took out 1 card, there's now only 51 cards left in the deck. So the first time, we're always assuming that I drew a king already. So this time, when I count how many queens are left, there are still 4 queens left in the deck. So then 4 out of 51 is what I am multiplying by. So multiplying these things together, I end up with 16 over 2,652. Okay, so there's my probability. Again, I don't need to reduce. I want to do another similar question, just this time getting like 2 kings in a row. So probability of a king and then another king. So 2 kings in a row. So if I were to do it this way, again, not replacing the first card, then the first card that I draw, I want it to be a king. There are 4 kings out of the 52. But then the second time, since I'm not putting my first king back in, now there are only 51 cards left in the deck, and I already took out a king. So how many kings are left in the whole deck of cards? Only 3. Because I already took one out and I didn't put it back in, now there's 1 less king and 1 less card in total. So this way, I end up with a probability of 12 out of 2,652. Okay. Okay, I want to do another example using our multiplication rule. This time we're going to deal with independent events so that the first event that happens doesn't affect the next. So in this example, we've got Spongebob jellyfishing in jellyfish fields, tra-la-la. So he usually has 40% chance of catching a jellyfish each day he goes to jellyfish fields. So each day, meaning like it's not going to change each day. Okay, so it's going to be 40% each day, which means it's going to be independent because the probability is not changing from day to day. Part A, find the probability that Spongebob catches a jellyfish 4 days in a row. So if he's catching a jellyfish 4 days in a row, really that means the first day he catches a jellyfish, and then he catches a jellyfish again, and then he catches a jellyfish again on day 3, and then day 4 he catches another jellyfish. So that's like 3 and thens. So you're multiplying multiple things here because there's so many and thens. So please enjoy my pictures of jellyfish. And so if he is 40% probability or 40% chance of catching a jellyfish, then we would need to multiply 40% 4 times in a row. So 40% means we're going to turn this into a decimal first. So moving the decimal place to the left 2 times would give us a decimal of 0.40. So that's the first day. And then 0.40 again for day 2, 0.40 again for day 3, and 0.40 again for day 4. So multiplying that all together, we get 0.0256. Which means, if I were to write this out as a decimal or as a percent, this would be like, if I move the decimal place 2 places to the right, 2.56% of him catching a jellyfish 4 days in a row, which is kind of low, but also 40% means that he's not very good at jellyfishing. So, okay, so you can, though, just leave your answer as a decimal. If you want to change it into a percent, that's cool too. So 2.56%. Just make sure if you turn it into a percent that you actually include the percent sign. Otherwise, 2.56 would not be a probability at all, because remember, probabilities have that rule where it has to be a number between 0 and 1. So 2.56 without the percent sign means that it's not a number between 0 and 1. Alright, so for part B, we want to find the probability that he doesn't catch a jellyfish 4 days in a row. So no jellyfish for any of the days. So if we do that, we know we're going to have to multiply 4 times again because we're talking about 4 days in a row. So if he has a 40% chance of catching a jellyfish, then he should have a 60% chance of not catching a jellyfish, because those are our 2 options. Either you catch it or you don't. And remember, everything in a sample space always has to add up to 100%. So here, for him to not catch a jellyfish on day 1, it would be 60%. Then we're going to multiply that by another 60% for day 2, for day 3, and for day 4. Okay, when we do that, we end up with 0.1296, or 12.96%. So like almost 13% of him not catching a jellyfish 4 days in a row. And again, I don't care whether you write your answer as a decimal or a percent. Okay, finally, last example. Find the probability that he catches that he catches at least 1 jellyfish within the 4 days that he goes. So we just want him to feel a little successful, okay? Basically, if you just want to catch at least 1, at least means like 1 or more. So we just want to make sure he doesn't catch none, because that would be really sad. If he left empty-handed 4 days in a row, that would be so sad. So at least 1 means that you just don't care about the none, or for him to not catch any jellyfish. If you remember your complementary probabilities, complement is like the opposite. So we basically want the opposite of none. So at least 1, so catching at least 1 jellyfish is the same as the probability of not catching none of them. So whenever we do the opposite, we would just subtract by 1. So if I can find 1 minus the probability of none, this would end up being 1 minus the 0.1296 that I got in part B. Because remember, in part B, I just found the probability that he doesn't catch any jellyfish. So that would be the probability of none, not catching any jellyfish. So subtracting that, I get 0.8704, or 87.04% of him catching at least 1 jellyfish within the 4 days. Not bad. This is good. This is hopeful for him. Okay, so basically, one nice example that, one nice formula that's good to know is anytime you're being asked about at least 1, the formula is like 1 minus none, which also rhymes. So at least 1, 1 minus none. So anytime a question asks you for at least 1 of something, then take 1, subtract out the probability that you get none. That's it for this section. Thanks for watching. Bye.